Questions 8 through 10 on the 2015 Grade 12 Euclid Math Contest. For some positive integers k, the parabola with equation y is equal to x squared over k minus 5 intersects the circle with the equation x squared plus y squared is 25 at exactly 3 distinct points a, b, c. Determine all such positive integers k for which the area of ABC is an integer. Well, let's draw a little diagram and try to understand this question. So we have some sort of a coordinate plane in existence, and that circle x squared plus y squared is 25 obviously is centered at the origin, so it's something like this. And then you've got some parabola, and it's going to touch in exactly 3 distinct points. So what I'm thinking is going to be something like this, like that. So 1 point here, 1 point there, 1 point there. So 3 distinct points. And those 3 distinct points, when you join them, obviously, will form a triangle. So what we can do is just join those 3 and make that triangle. So like that and like this. And they have called those points A, B, and C. So this I call A, B, and C. Now the coordinates of B, since that's on the y-axis, that's going to be 0 and some B, I'll just call it B. And then the coordinates of C and A, well, those I don't know yet, so we'll figure that out. All right, so here we go. Our equations are y is equal to x squared over k minus 5, and x squared plus y squared is equal to 25. So these have to be equated, so we have to set them equal to each other. So what we can do is we can substitute one into the other. That's also valid in order to figure out the solutions. So if we isolate for x squared in that one, we can take that value and sub it into there. So let's do that. That would mean 25 minus y squared over k minus 5. And then if we solve this, multiply through by y, and multiply through by k, I should say, and put everything on one side, we get yk is equal to 25 minus y squared minus 5k. And when you put everything on one side, you get y squared plus yk plus 5k minus 25 is equal to 0. Okay, well at this point it's a quadratic, so I've got to use the quadratic formula. So y is equal to minus b plus or minus the square root of b squared minus 4ac, and c is 5k minus 25. Okay, and of course that's all over 2 times a, which is 1 in this case. So simplifying this, we get k squared minus 20k plus 100, and that factors very nicely. It factors into k minus 10 squared. So that's going to mean, since we have k minus 10 squared under the radical, it just becomes k minus 10. So it works out very nicely. And then this will give me 2 roots, plus or minus. The plus one just gives me, the k's would cancel, so it would be negative 10 over 2, which is negative 5. And then the negative one would be minus 2k minus 10, minus 2k, I should put that in brackets, plus 10 over 2. So when you divide by 2, it'll be just minus 5 minus k plus 5. All right. So that means that the minus 5 is here. So this is 0 minus 5, which makes perfect sense, since we could already know that because the radius of the circle is 5, right? So we already know that this is going to be minus 5, but we've validated that. But these two are now very important. This is going to be, the y value is 5 minus k right here. 5 minus k. And then on this side, again, the y value is 5 minus k. Now our task is to figure out the x values. Well, to get the x values, we can substitute this into either this one or this one, whichever one you feel is easier. Both of them are pretty much the same, so I'll just use either one. It doesn't really matter. So if you sub it in the first one, we get 5 minus k is equal to x squared over k minus 5. Bring the 5, I'll multiply through by k, I think that will be easier, and you get 5k minus k squared is equal to x squared minus 5k. Bring the 5k over and you get 10k minus k squared is equal to x squared, and therefore x is equal to plus or minus the square root of 10k minus k squared, like that. So that means this guy here is going to be positive 10k minus k squared, and this one obviously is the negative one, 10k minus k squared square root, but the negative one. All right, now we're ready for the final step, which is the area. The area of that triangle obviously is 1/2 base times height. The base is the distance from there to there, and that's just going to be 2 times the value of x, which is 10k minus k squared root. And then the height is from there to there, which is going to be 5 minus k minus 5, which would be plus 5, like that. All right. So this becomes, well, the 1/2 and the 2's cancel, and I'm going to factor a k just to make the math a little bit easier. 10 minus k, that's still all under the square root, and this is 10 minus k. Okay. Now at this point, now that I've got this simple formula, we have to make a table and try to figure out what values of k will give an integer value for the area. And remember, they actually told us in the question, they gave us a hint that k is between 1 and 9. Actually, what I really meant by that is that we can conclude that k is less than 10 because of this, right? Area is always positive, and the only way that's going to be positive is if k is less than 10. And they have told me that k is an integer, right? Positive integers k. So k is going to be an integer, but it's got to be less than 10. So that's what I really meant to say. Okay, well, if it's less than 10, it's got to be either 9, 8, 7, 6, 5, 4, 3, 2, 1. And for each of those, here's my area formula. I just got to sub in the values of k and figure it out. So we can do this pretty quickly. Well, I'll let you do it. I'll just fill it in the table. 27, 32. All I'm doing is putting in the value of k into this formula to figure out the area. And the ones that are integers, those are the ones that I want. So when you plug in values of k, you get the following, right? And this can be done pretty quickly. You can do it in your head, or well, most likely you're going to do it on a calculator. So there we go. So as you can see, the integer values occur, the integer values for the area occur when k is equal to 9, 8, 5, 2, and 1. So the values of k for which the area of that triangle is an integer are 1, 2, 5, 8, and 9. And that is what they're looking for. In the diagram, triangle XYZ is isosceles with XY equal to XZ equals A and YZ equals B, where B is less than 2A. A larger circle of radius R is inscribed in the triangle. That is, the circle is drawn so that it touches all three sides of the triangle. A smaller circle of radius small r is drawn so that it touches XY, XZ, and the larger circle. Determine an expression for large R over small r in terms of A and B. This diagram is at the heart of the question, so let's enlarge it and let's try to label as much as we can. The first, I will draw a line all the way from top to bottom. Then I will draw the radii that touch the tangent points, and those will be approximately like that. And I believe we should be okay, but one more line from the center to Z, and that should be sufficient. And then let's draw the fact that these are going to be right angles, since those are tangent points. And now let's label as much as we can with some variables. Well, from here to here is R, and from here to here is R. Those are radii. This is small r, this is small r. Similarly, that is small r, this is large r. And then the distance from here to here, that is not known, so I will give it a distance. I will call it h. So in particular, I'm referring to the distance from here to here. That I will just call h. And then on the base, it's b, but when you draw a line perpendicular, it chops it in half. So the distance from here to here will be b over 2. And here's an important point. From z to that tangent point is the same distance as z to that tangent point. So that means this distance right here is also b over 2. And that should be sufficient for us to create similar triangles and equate the sides. So we are now going to proceed with similar triangles. Now I'm going to label a couple of angles just to illustrate what the similar triangles are. So this angle right here I will call theta, and therefore this guy here, that angle in there, is going to be 90 minus theta. And that really is talking about that big triangle right here, since this is 90 degrees. And then you'll get some similar triangles. You'll get that this one is similar because it has the same angles. This is theta. And the same story holds true for that triangle, where this angle is theta. All right, so that means we've got similar triangles and the ratio of the sides will be the same. So for the big one, the base over the hypotenuse is b over 2 over a. And that is the same as those two corresponding sides on that triangle, because that is a similar triangle. So the base, which is r in that case, over the hypotenuse, which is big R plus small r plus h. And same story holds true for that smaller triangle, since it's also similar. The base, which is small r, over the hypotenuse, in that case, which is h. So hopefully so far there's no tricks. Now I've got a few choices, but I'm going to go with this one here. That equation I'm going to use to try to get a relationship. So I'm going to isolate for h. So let's try to do that. Cross multiply, and we get r plus r squared plus h squared, like that. RH, that should be. And then we will bring the h's over to one side, and hopefully that will let me isolate for it. So that comes over. And then I can factor out the h, and I'll get big R minus small r, and this side becomes or remains r plus r squared. And then of course now I can isolate for h. Big R small r plus r squared all over big R minus small r. That's pretty good. All right, now where do I go from here? Well, I've got to get a and b into the equation, because in the end I've got to get this in terms of a and b. All right, so obviously I now have to turn my attention to this. I've got to use that somewhere. So I'm going to use that and this. I think that will allow me to get r over r in terms of a and b. So let's do that. So now I've got b over 2 over a is equal to r over h. But h I just got in that form. So let's do the math here. B over 2, invert and multiply, and I get 1 over a. And then here I get r over h. But instead of dividing by h, I'll just invert and multiply by this guy. So it will be r minus r over r plus r squared. All right. So now we pretty much boiled down the question to this. And this, if done properly, should give me what I'm looking for, where I have to get some sort of expression where big R over R in terms of A and B. Something like that. Okay, so here we go. Let's do this carefully without making any algebraic mistakes here. So B over 2A. And this side looks like, well, this R will cancel with R's in that. So very quickly, we get minus R over big R plus R. All right, so that's pretty good. Okay, so at this point, the good news here is that no fancy algebraic tricks are needed. All we need to do is just simple cross multiplication. That will be BR plus B small r, and the other side will give me 2AR minus 2A small r. Put everything with r on one side. So 2AR, I'll bring the minus BR over, and put everything with the small r on one side, so plus 2A small r. Factor out the big R, we'll get 2A minus B. Factor out the small r, and we get B plus 2A. And then now let's try to get that big R over small r. And when I do, on this side, it'll be 2A plus B over 2A minus B. And there we go. Without any real tricks, we're able to get big R over small r in terms of A and B. And in particular, it's 2A plus B divided by 2A minus B. And that completes the question. Consider the following system of equations in which all logarithms have base 10. If a is negative 4, b is 4, and c is negative 18, solve the system of equations. All right, so what we will do is we'll make some substitutions to make our life easier. I'll let the log of x equal a, and the log of y equal b, and we'll let the log of z, or log of, z equals c. Okay, so substituting those, and then of course we've got a log rule. I'm sure many of you, well, all of you should know this, that if you have the log of 2 multiplied by each other like that, it's really can be written as the log of m plus the log of n, with the same bases, of course. Okay, so let's do the substitutions here into these three equations. We're going to have ab minus 3 log of 5 plus b. I've already applied that log rule, minus the log of 8 plus a, and that equals negative 4, since a is negative 4. And in a very similar way, the next one becomes bc minus 4 log of 5 plus b minus the log of 16 plus c, and that equals 4, since b is equal to 4. And then the next one, the last one, third one, ac minus 4 times the log of 8 plus a, and that is equal to, if we continue, minus 3 log of 625 plus c, and that is equal to negative 18, since c is negative 18. All right, so now what we have to do is we have to put everything on one side and kind of take it from there. So let's do this one step at a time. We've got 3 of these. So each of these, I think, or at least my hope is that it will work out very nicely. So the first one right here, we've got AB minus 3 log 5 minus 3b minus the log of 8 minus a is equal to negative 4. And then what I'm going to do is just keep the letters on one side and put all the numbers basically on the other side. So it'll be AB minus 3b minus a, and on this side we'll get minus 4 plus 3 log 5, which is essentially just a number, plus the log of 8. And then if you get your calculator out and you do this math, you will be pleasantly surprised to find out that that equals 3. So you just get minus 4 plus 3. And on this side, of course, this is AB minus 3b minus a. So we can now have equation number 1, which is that AB minus 3b minus a is equal to negative 1. So it works out very nicely. Okay, we do the same sort of story now with this guy. That one, BC, is equal to, well, minus 4 log 5 minus 4b minus log of 16. I think there's a 4 missing here, yeah. Actually, there isn't. I'm putting unnecessary things. Log of 16 minus c is equal to 4. Okay, so as before, I put all the numbers on one side and all the letters on one side. So it'll be BC minus 4b minus c, and then on the other side, we'll just put all the numbers. So it's going to be 4 plus 4 log 5 and plus that log of 16. And you'll be pleasantly surprised or happy to know that those guys just add up to 4. So this just becomes 4 plus 4 is equal to BC minus 4b minus c. So this gives me my second equation, which is that BC minus 4b minus c is equal to 8. Okay, now we got the hang of it. Let's do the last one. AC, let's see here, minus 4 log 8 minus 4a minus 3 log of 625 minus 3c is equal to negative 18. And as before, let's put all the letters on one side. So we have AC minus 4a minus 3c, and this side will become minus 18 plus 4 log 8 and plus 3 log 625. And these guys, when you add them up, equal 12. So again, we get a very nice result, not messy at all. It works out in a way that we just have integers to deal with. We don't have any decimals and all that stuff. So this now gives me another very nice equation that AC minus 4a minus 3c is equal to negative 6. All right, so far, perfect. We're doing great. Now at this point, what you have to do is we have to solve, right? So basically, it's 3 equations, 3 variables. We've got to solve them, and you can definitely do that. So from the first one, equation number 1, we'll try to isolate. We'll try to get one variable in terms of another. So from that equation, if I factor out an a, I get b minus 1. And then I get on the other side 3b minus 1. And therefore a, very quickly, is equal to 3b minus 1 over b minus 1. From the second equation, this guy, again, we factor out a b, and you get c minus 4. And put the c over on the other side, so you get 8 plus c. And therefore b will be 8 plus c over c minus 4. And then this one, let's see, we get a in terms of c. I think that will be helpful. So I factor out an a, I'll get c minus 4. And then there'll be minus 6 plus 3c on this side. So a is equal to 3c minus 6 over c minus 4. All right, great. So again, we have some very good, easy to work with variables. Now, all I have to do is start subbing in. And what I'll do is I will use this one. I think this is sufficient. So if I used ab minus 3b minus a is equal to negative 1, I can solve. I can put a in terms of c and b in terms of c, right? These two, and solve for c. And once I solve for c, I can plug those back into these guys to solve for a and b. And then I'll be ready to get my values for x, y, z. So a little bit of work, but we can definitely do that. All right, so a is 3c minus 6 over c minus 4. B is 8 plus c over c minus 4. And then minus 3b, 8 plus c over c minus 4. And then minus a, which is 3c minus 6 over c minus 4 is equal to negative 1. All right, so now we've got a little bit of algebra, but as long as you don't make any mistakes, you should be okay. So let's multiply this out. When we do, we get 24c plus 3c squared minus 48 minus 6c. And here we have c minus 4 squared. And then this guy over here, on this side, we will have, let's see here, 6 minus 24 minus 3c, and then we have minus 3c plus 6, and that's all over c minus 4. But I want to get a common denominator, so I have to multiply top and bottom by c minus 4, and this is of course negative 1. Okay, so this remains the same. 24c plus 3c squared minus 48 minus 6c. But I can combine those, right? The 24c and the minus 6c can be combined to give you just 18c. And then I'm going to cross multiply. So instead of having it in the denominator, I'm going to bring it over to combine with the negative 1, cross multiply it. So it'll be just negative 1 times c minus 4 all squared. And then this guy, let's see here, this becomes plus minus 18 minus 6c, like that. And then I've got to multiply by c minus 4. Okay. So far, hopefully I haven't made any algebraic mistakes. So this is 18c plus 3c squared minus 48. And then if I multiply this, I will get minus 18c plus 72 minus 6c squared plus 24c. And on this side, I've got to expand this guy. So it's going to be minus c squared plus 8c and minus 16, right? Because I've got to multiply by negative 1. Okay, now let's put everything on one side if we can. So let's see here. Let's try to combine. We've got plus 3 minus 6, so the minus 3, when you put the minus 3 on this side, if you're adding, it will become 2c squared. Then the c's, this 18c cancels with that. And the 24 I'll bring over here. So it'll be 8 minus 24, which will be minus 16c. And the numbers, let's see here, minus 48, 72, and minus 16. When you combine those, it's minus 40. Okay, very nice. So divide through by 2, and I will get this. And then now I'm pretty sure I can factor this. C 10 to negative plus. Great. So C is 10 and negative 2. See what I mean? Hard work pays off. So now I can go back and plug it into here. So these formulas I will use to figure out the values for A and B, since I have my C. So C is is 10 or negative 2. So if you remember, B was equivalent to A plus C minus 4. So when you sub in these values, you will get the following for B. You'll get B is equal to either 3 or negative 1, respectively, for 10 and negative 2. And if you remember, A was equal to 3C minus 6 over C minus 4. So when you substitute these values in, you will get, for example, 30 minus 6, which is 24 over 6, which is 4. And then for negative 2, it would be minus 12 divided by negative 6, which is positive 2. So my triplets, A, B, C, triples, whatever you want to call them, are 4, 3, and 10. And the other one is 2, negative 1, and negative 2. Right? But remember, we need x, y, z. The question is so long, you might have even forgotten what the substitutions were. I'll remind you, the substitutions were that the log of x was a, the log of y was b, and the log of z was c. So using those substitutions, we can easily get the values for x, y, and z. X, y, z, using these for a, b, and c, are 10 to the power of 4, 10 to the power of 3, 10 to the power of 10. That's my first triple. And the next triple, of course, would use those values for a, b, c. It would be 10 to the power of 2, 10 to the power of negative 1, and 10 to the power of negative 2. And there you go. That completes the question. Part B. Determine all triples, A, B, C, of real numbers for which the system of equations has an infinite number of solutions, x, y, z. All right. So very similar to what we did in Part A, I want to go back and refresh your memory that we had found those equations. If you remember, after all those substitutions, and those equations were a, b minus a minus 3b was equal to a plus 3, where this is the a. I'm not going to substitute values for a, b, and c because now we have to actually find them. And very similarly, we have another one that bc minus 4b minus c is equal to b plus 4. And then we had, of course, the third one, which was ac minus 4a minus 3c is equal to c plus 12. So that's pretty much from Part A. We had figured that out. The only difference is that we had substituted values for a, b, and c. This time I'm not going to do that because now I've got to figure out what is a, b, and c. So when we work with these, the first thing I will do is rewrite these. I want to factor it. So I think I can factor it. AB minus A and minus 3B. And then to bring this 3 over, minus 3 is equal to A. And if I were to just rearrange this ever so slightly, it would be able to factor. Instead of this minus 3, I'm going to put plus 3 minus 6. right? 3 minus 6 is the same as minus 3. But when I write it like that, I'll be able to factor it. Notice this a factors out. I get b minus 3, like that. Or b minus 1, actually. And then if I, on this side, factor out a 3, I'll get b minus 1. And then this minus 6 I can put on the other side. So a plus 6. So this now factors into a minus 3 and b plus minus 1, like that. And that's a plus 6. So hopefully that wasn't too difficult to understand. Just a little bit of manipulation was involved. Not too much. Okay, let's do the same thing over here. So we got bc minus 4b minus c, and then minus 4 is equal to b. Again, I have to manipulate this ever so slightly to get a situation where I can factor. So instead of minus 4, I'm going to put plus 4 minus 8, which is essentially the same thing, but allows me to factor these guys. So factoring, I get b c minus 4, and then on this side we have minus c plus 4 and b plus 8 if I bring the 8 over. So this factors into b minus 1 and then times c minus 4, like that, equals b plus 8. All right, so hopefully you're getting the hang of this. And then now we'll do very similar kind of factoring on this guy. This is ac minus 4a minus 3c minus 12 is c. So ac minus 4a minus 3c, and then plus 12 minus 24 is equal to c. So again, factoring, I get a c minus 4, and then here I'll get minus 3 c minus 4, and then on that side it'll be c plus 24, and this side of course factors into a minus 3 and c minus 4 is equal to c plus 24. All right, so I've got my 3 equations. Now, at this point we have to discuss this a little bit. So far all I've done really is factor them in a way that I can now work with. So what I'm going to do is just make some substitutions. Let a minus 3 equal p, let b minus 1 equal q, and let c minus 4 equal r. It'll just make things a little bit easier. So now these equations basically become p times q is equal to a plus 6. This one becomes q times r is equal to b plus 8. And this one becomes p times r is equal to c plus 24. All right. So we're getting it down into something very digestible. Now let's take this, this, and this, those 3, and multiply them all together. So on the left side, you'll get p squared, q squared, r squared. And on this side, you'll get a plus 6 times b plus 8 times c plus 24. Okay, so now we have to talk about this. This is where the question has to be discussed. What type of cases? Case number 1 is when this part, we consider it being equal to 0. Actually, let me make the first one less than 0. I think that will be a little bit easier as a first case. If it's less than 0, that means this has to be less than 0. P squared, q squared, r squared is less than 0. Well, that's impossible because this is a perfect square. It's either equal to 0 or it's positive. There's no way it can be less than 0. So if we let this be less than 0, it would give you no solutions for p, q, and r. Okay, so case 1 we eliminated pretty quickly. case 2. Case 2 is when you have a plus 6, b plus 8, and that c plus 24 greater than 0. All right. So when that happens, that means that p squared, q squared, r squared is going to be greater than 0. And when we take the square root of it to get just PQR, it will basically be giving plus or minus the square root of this whole thing. A plus 6, b plus 8, and c plus 24. And that's going to be P times Q times R. Now, when that happens, you'll notice that this will give you a finite number of solutions, not infinite, when you solve like this. So for example, P would be plus or minus A plus 6 times B plus 8 times C plus 24 over QR, right? And as you can see, that is 2 solutions. 2 is not infinite. 2 solutions for P. And then similarly, when we do the same sort of things, you would get 2 solutions for Q and R. So since 2 is certainly not infinite, case 2 doesn't give us infinite number of solutions. All right, so now we move to case number 3. Case number 3 is the only thing that's left, which is A plus 6, B plus 8, and that C plus 24 is equal to 0. That's the only other option we have. Okay, so this has to be discussed, and off we go. So the first thing is if only one of these is equal to 0. So for example, I'm going to just let A plus 6 equal 0. And then that means B plus 8 is not equal to 0, and C plus 24 is not equal to 0. All right. So recall what is this whole thing. It was P squared, Q squared, R squared, and that was equal to this whole thing, A plus 6 times B plus 8 times C plus 24. And recall what each individual was equal to. A plus 6 was equal to P times Q. Now we have set that to be 0. So if that's 0, that means either P is 0 or Q is 0. Correct? So therefore, we have to look at these two guys. And B plus 8, if we recall, that was equal to QR. And C plus 24, that was equal to PR. So if P equals 0 or Q equals 0, then that means that either this is equal to 0 or this is equal to 0, right? If these two are equal to 0, one or the other is equal to 0. If P was equal to 0, then that would make that equal to 0. If Q equals 0, it would make that equal to 0. But here's the problem. We've already told this. We've already said that B plus 8 and C plus 24 are both not equal to 0. So what we basically have created is a contradiction. And therefore, we cannot have a scenario where only one is equal to 0, as I have shown. So this doesn't work. So the next scenario is if 2 are equal to 0, meaning 2 of those 3 factors. So for example, A plus 6 is equal to 0, and say B plus 8 is equal to 0, right? That would be an example of 2 being equal to 0, and therefore C plus 24 is not equal to 0. Okay, so that is how we're going to proceed with this one. Okay, so what is A plus 6? If you recall, it's P times Q. And what is B plus 8? If you remember, B plus 8 is Q times R. If those two are equal to 0, that means Q must be equal to 0, right? That's the only way that both of those can be equal to 0. And then we explicitly said that C plus 24 is not equal to 0. And C plus 24 is P times R. So that means P does not equal 0 and R does not equal 0. Okay, so that means when we have any triple of the form P, Q, which is 0, and R, this will give me a solution. Right? I hope that makes sense. So, that means A plus 6 is 0. So A will be negative 6. B plus 8 is 0. So B will be negative 8. And C is anything. C plus 24 is not 0. So C can be anything. The only thing it can be, the only thing it can't be is negative 24. So our triple ABC is negative 6, negative 8, and C. For any C except C equals negative 24. So since C can be anything, we have an infinite number of solutions for A, B, and C, right? And each A, B, and C, if you remember, if you go way back, each A, B, and C right here will give an infinite number for X, Y, Z when we sub them back into this system of equations. So that is a key thing to remember in this very long question. And in a very similar way, we can also show that ABC can also be minus 6B and minus 24, as long as B is not equal to minus 8. And we can also show in a very similar way that ABC can be A minus 8 and minus 24, where A is not equal to minus 6. So since we have infinite number of C's, B's, and A's, each of those will give you an infinite number of solutions for X, Y, Z. So these triples right here will provide an infinite number of solutions X, Y, Z to the original system of equations. Now there's one more, and that is if all three are equal to 0. So that means A plus 6 is 0, B plus 8 is 0, and C plus 24 is 0. And obviously if you solve for those, you'll get ABC is equal to minus 6, minus 8, and minus 24. And that will also give you an infinite number of solutions. And the reason is because A plus 6, if you remember, was PQ, and we're saying that A plus 6 is 0. And then B plus 8, if you remember, was QR, and we're setting that equal to 0. And C plus 24, which was PR, we're setting that equal to 0. And this will be true if P equals 0 and Q equals 0. So R can be anything. So that means if we have PQR as 0, 0, and R, that kind of a triple, that will give an infinite number of solutions because R can be anything. So that also means that this is going to help give another scenario where you have an infinite number of solutions. But what's interesting is this is actually included in this. For example, when C is minus 24, it's of that form is what I'm trying to say. All right, so basically any triple that's of the following forms: minus 6 minus 8c minus 6b minus 24, a minus 8 minus 24, and then the last one, which is minus 6 minus 8 minus 24, they will all provide an infinite number of solutions xyz to the original system of equations. For each positive integer n greater than or equal to 1, let Cn be the set containing the n smallest positive integers, that is, Cn is equal to 1, 2, up until n. For example, C4 is 1, 2, 3, 4. We call a set F of subsets of Cn a Faroni family of Cn if no element of F is a subset of another element of F. Consider A 1, 2, 1, 3, 1, 4. Note that A is a Faroni family of C4. Determine the two Faroni families of C4 that contain all the elements of A and to which no other subsets of C4 can be added to form a new larger Faroni family. Okay, so let's explain this question first. C1 is just 1, right? C2, basically according to this definition, is 1, 2. C3 is 1, 2, 3. And the one they give you, C4, is 1, 2, 3, 4. So that's pretty easy to understand. But then we have to figure out all the subsets. Okay? Subsets of this guy, well, there's only one. That's it. Subsets of 2, you can have either 1, you can have 2, or you can have 1, 2. Like that. Subsets of these, we have a few more subsets here. 1, 2, 3 individually, or you can have 1, 2, you can have 1, 3, or you can have 2, 3, like that, or you can have the whole thing, 1, 2, 3. I mean, that is the entire set, but it can be a subset, I guess, if you really wanted to. Now we get to this one, and look, this one has a few more, right? Individually, you'll have 1, 2, 3, and 4. If you look at two of them, you have 1, 2, 1, 3, 1, 4. You'd have 2, 3, 2, 4, and then of course you'd have 3, 4. And then in terms of the ones that have 3 in them, it'd be 1, 2, 3, 2, 3, 4, 1, 2, 4, and 1, 3, 4. And then of course the full one, 1, 2, 3, 4. But that's technically not a subset, right? Because that's the full set. But I'll just write it in there. What the heck? Okay, so now what do they want us to figure out? What they want you to figure out is the Faroni families. So they're saying that there are, how many? 2 Faroni families of C4. So we'll call it family 1 and family 2. So the first one, they've actually given you some of the elements already. 1, 2, 1, 3, and 1, 4. And they're saying that these families, there's 2 of them. They want you to find them. Okay, so what we have to do is look at what possible candidates we have to add. So we've got to look at this big set to add. And I'm going to get rid of this one because that's technically not a subset, right? It's the entire set. So from these ones, I've got to add some to these. Okay. Can I add these guys? No, because that doesn't match the definition. The definition is pretty strict that no element of F is a subset of another element of F. That's very important. No element of F is a subset of another element of F. So for example, if I put this 1 in here, it would become a subset of this, and that's not allowed. You see what I mean? So none of these individuals could go. So we can just cross those out. Now, what about if I put one of these guys? Well, this is already in there, so is this one, so is this one. How about these ones? Can I put them in there? I think so, because if I do that, we don't run into any problems. And in particular, it's going right back to that sentence. No element of F is a subset of another element of F. So that's fine. This is my first Faroni family, F1. But they're saying there's two. Okay, well, how can I get another one? Well, I've exhausted these guys. These are all done. So this is all done. So I'm assuming that to get F2, I've got to look at these guys. Okay. So can I put 1, 2, 3? If I put 1, 2, 3. No, because 1, 2 is a subset of 1, 2, 3. And remember the fundamental rule that no element of F is a subset of another element of F. Okay, so 1, 2, 3 is out. Can I put 2, 3, 4? And after careful thought, the answer is yes, you can. In fact, that's the only one you can put from this list, because all the other ones would run into the problem that you'd have an element that's a subset of another element. And that's it. Those are my two Faroni families. And these are maximized. You can't add any more elements to it. So the first one is right here, and the second one is right there. And that satisfies the condition of the question that we have two Faroni families that contain all the elements of A, which is right here, and to which no other subsets of C4 can be added to form a larger Faroni family.